There are a lot of problems that lend themselves well to being modeled and solved using quadratic functions. You will encounter a few that are somewhat contrived, involving numbers with various characteristics or conditions like certain sums, but there are some very nice real-world problems, and the one we're going to look at right now is a revenue problem. And let's say, for instance, that Grouse Mountain has a summer pass that costs $80, and at that price they sell 2,200 passes. And then for every $5 increase, they sell 100 fewer passes. What price will maximize their revenue? Well, let me just comment on this for a little bit. First off, the statement for every $5 increase, they will sell 100 fewer passes implies that the demand for the passes is linear. So if you increase by an additional 5, you will sell 100 fewer. So every $5 increase, you drop by 100. And conversely, if you drop the price by $5, you would increase the sales by 100. Now, this sort of linear demand is used a lot in business and economics, and it's pretty reasonable in a certain range. It breaks down a little bit at the extremes, as we're going to see later on. I'll comment on that, but usually you're not really worried about the extremes, and it makes the math a lot easier, which is highly desirable. So we're going to look at two different ways of solving this problem. The first way is a very direct, quick way, but I refer to it as sort of a black box, meaning that you'll initially not really know where everything's coming from, but you may learn the steps, and if you learn the steps, you'll be able to get the answer. But there's problems all along the way. You don't really get a deep understanding of the problem. If you misremember the steps, you're going to set it up incorrectly. Even if you do remember the steps correctly, you may end up interpreting the answer incorrectly. And so there's some problems all along the way. The other way is a slightly longer way, but it really will give you a much deeper understanding of the problem, and it'll actually also allow you to think about solving the problem without resorting to technology like a graphing calculator. So regardless of which method you're going to use, I would say the first step is to make a little table summarizing the data given. So you're given a price initially of $80 and a sales level initially of 2,200. And we're looking for revenue. Well, revenue is just price times sales. So revenue in this case is 80 times 2,200, which is 176,000. So they're making 176,000 at that price level. And then if they increase the price by $5, that would give you a price of 85, and you'd lose 100 sales, so you'd be down to 2,100 in sales. But when you go to calculate the revenue, you find out that you're actually at a higher revenue of 178,500. Now, before you start doing the calculations, it's not entirely obvious that by increasing the price, you're going to increase the revenue. All right, the sales might drop sufficiently that you actually have a lower revenue, and so you never really know with these problems which direction is going to be best. But when you see this, you know that the price that maximizes revenue is certainly going to be higher than 80. It could actually be somewhere between 80 and 85, or perhaps 85 itself is the price that maximizes revenue, or perhaps it's a higher price yet still. Now, here's as I said, a very quick way. Revenue, as I said, is simply a product of price and sales. So what we're going to do is come up with an expression for price and an expression for sales. The expression for price is going to start with the base price, which is 80. And then we have 80 plus 5x, where x represents the number of price increases. Now, it's not a price, so don't use P. It is simply a certain number of price increases. So in other words, with one price increase, you'd have 80 plus 5 times 1, 85. It would be the second line of that table. Similarly, sales starts out at 2,200. And then with a single price increase, you drop by 100. So this is going to be minus 100x. So if you let x equal 0, you should have the base case, the first line of that table, 80 times 2200. If you let x equal to 1, you should have the second line of that table, 85 times 2100, which is what we have. Now, at this point, you're going to plug this into a graphing calculator or some sort of graphing software. And I'll use the TI-83. So hit y equals if you don't already have it up, and then you can enter it exactly the way it looks, 80 plus 5x and 2200 minus 100x. Now, if you just hit graph and you've got the default window settings, you really aren't going to see anything here. So it's really helpful to take a look at the table of values first. And what we can see is when x equals 0, we get a revenue of 176,000, which is exactly the first row of our table. And the second row of our table there is an x equal to 1 with a revenue of 178,500. So at least that's sort of confirmation that we've actually got this set up correctly. You can see that the revenue keeps on going up. And the fourth row with x equal to 3, you get a revenue of 180,500. That seems to be our peak. Now, might not turn out to be exactly the peak, although you can tell by the symmetry of the table that this is the peak. But let's use the graph and find the vertex just to make sure. You're going to have to set the window settings, though, to something quite different. Obviously, we need to increase the y max considerably. So I'm going to change the y max to 200,000 so I can see the top of this parabola. And then I'll have the y scale, which tells me the tick marks every 20,000. And then I can hit graph, and I can see the top of the parabola here. And I'll use second calc max. And the left bound is fine. The right bound, I need to go to the right of the vertex. And then I hit enter. And then for the guess, just hit enter again. And you get a maximum of x equal to 3. Whenever you see a whole string of 9s like that, 2.999999, you can assume that it's 3. And sure enough, the y value, which is our revenue, is 180,500. So we've got that vertex at 3, 180,500. Now, here comes the interpretation part. And I have actually seen this messed up in textbooks that use this method because it is a little tricky to interpret this. So what do these two numbers represent, the 3 and the 180,500? Well, the 3 is x, which is our number of price increases. And because it represents a vertex or a maximum, we can put a little star beside it. So it's x star, if you like. And the y is revenue, so it's revenue star. But what you're typically going to be asked is not just the revenue. You'd actually like to know, as this question is asking, what's the price that maximizes revenue? And this doesn't tell us that directly. So where do we get price from? Well, price, we use that expression in the equation above, is 80 plus 5x. And if we want P star, which is the price that maximizes revenue, we need to plug in X star, which is 3 in this case. So that's 80 plus 5 times 3, which is 95. And if we want S star, the sales that maximize revenue, well, that's going to be 2200 minus 100 X star, which is 2200 minus 300, which is 1900. And we could have got that 1900 another way. We could have just taken the revenue, 180,500, and divided it by the price. That should tell us the number of passes that we sold. So we know that the maximum revenue is going to be achieved at a price of $95. Now, it turned out in this example that the number of price increases was an integer. One of the mistakes that is made in some textbooks, as far as I'm concerned, is the rounding of that number to an integer. Well, there's nothing really limiting the business to selling the prices at $5 increments. So let's say this just happened to give us a vertex of 2.75, 2 3/4 price increases. Is it really impossible to do 2 3/4 price increases? No, because every price increase is $5, and you can break down the price of the pass to whatever you like. You don't have to sell it at 90 or 95 or 100. You can sell it for something in between there. And so that's one thing that it causes problems when I see this method used. Let's take a look at the longer method that I really much prefer, and I think is worthwhile learning. It starts off with actually thinking about the demand curve. So the demand curve is not really a curve at all in this case. It's a straight line, but that's pretty common in economics. They always call things curves, even if they end up being straight lines. And it goes down because as you increase the price, you sell fewer. So this is sales versus price. And really, you don't have to worry about any kind of accuracy here. The point of this graph is just to allow you to calculate the equation of this line without too much effort. We've got a couple of prices given, 80 and 85. And we have a couple of sales levels given, 2100 and 2200. So the slope, which is always going to be negative, is the rise 100 over the run 5. So it's minus 100 over 5, which is minus 20. Now, there's an economic interpretation to that slope, which is that if you increase the price by $1, you sell 20 fewer passes. Or conversely, if you decrease the price by $1, you sell 20 more passes. Now, we need to find not only the slope, but the y-intercept. The y-intercept you can find using traditional methods. Just set it up as y equals mx plus b, or you can reason it out. As I said, if you decrease the price by $1, you sell 20 more passes. So if you decrease the price from $80 to 0, you're going to sell 1,600 more passes, 80 times 20. So 1,600 plus 2,200 gets you to 3,800. Now, there's another point on this graph that's actually pretty useful, which is the x-intercept. In other words, how high do I have to set the price before I don't sell anything? In other words, it's too high. So we can use the same thing to find that x-intercept. If you increase the price by $1, you sell 20 fewer passes. So if you want to go from 2,200 all the way down to 0, you need to increase the price by $110. So 80 plus 110 takes you all the way out to 190. Now, why is this useful? Because as soon as you have that number, you basically have the answer to the question. Because you know that your revenue is going to be 0 if you set the price to 0. It doesn't matter how many you sell. If you're not selling them, if you're not charging anything, you're not going to make any money. So that's one of your zeros. And now you have just found the other 0, setting it to a price of 190. And the vertex is always going to be halfway between the two zeros. So halfway between 0 and 190 is 95, which is exactly the value we got in the previous calculation. So we do that really without resorting to a graphing calculator at all, and maybe not even resorting to a calculator, depending on how easy the numbers are. But let's see how it continues. If we did want to continue this and plug it into a graphing calculator, we don't want to plug this equation into the graphing calculator, which is sales. I'll divide this up so we don't get confused. We don't want to plug the sales function into the graphing calculator. The sales function is minus 20p plus 3,800, because that's just a straight line. We're interested in the revenue function. And the revenue function, again, is just sales times price, which, if you multiply the equation above by p, you get minus 20p squared plus 3,800p. And that is very obviously a quadratic function. Now, let's take a look at that on our calculator. So let's change the function. It's minus 20. You cannot use, oh, it's a bit flaky, I've got to restart it. You cannot use p, you have to use x. So it's minus 20. x squared entered in the calculator, plus 3,800. Well, that should be 100, not a 380 x. Let's correct that now. Okay, so p in reality, but when we plug it in on a calculator, we plug in x. Okay, so there we go. Now, again, you're going to have to take a look at the window settings, or rather the table, to get an idea of the window settings, because here the x value is very different. Here the x value is actually price. And so you would expect, for a price of 0, you have a revenue of 0. And you can see that as you go down, you increase the price, your revenue starts rising. 30,000, 40,000, 50,000, etc. And you could actually get a rough idea of the price that you need to maximize revenue just by going down this table. And this is normally what I do. I just sort of look for the point at which the revenue stops going up. You can see it's still going up, up, up. We're at $70, $80. And it's slowing down for sure. And sure enough, there at 95, it peaks out at 180,500. Now, you've basically got your answer right there. But if you did want to see a graph, what I would do is take that 95 and double it to get 190. And that's what I would set my window settings to. I would set the x-min to from 0 to 190. We'll put a tick mark every 10, let's say. And you can leave the y max and the y scale the way they are, 200,000 with ticks every 20. And then when you look at the graph, you see the full parabola there. So starting at a revenue of 0, going all the way up to the peak and going back down to a revenue of 0. When you do second calc max, you can take plug in the left bound, the right bound, and enter, and sure enough you get 95, 180,500. So the vertex is at 95, 180,500. And this is much simpler to interpret because we were graphing revenue as a function of price. And so, in fact, this is P star, the price that maximizes revenue. This is R star, the maximum revenue. The only thing we don't directly have is the sales at the maximum revenue, S star. But that's pretty easy because that's just simply the revenue divided by the price. And so you have 180,500 divided by 95, and that turns out to be 1900 as above. So I think actually with a bit of practice you'll realize that you don't even really need to resort to using the graphing calculator as long as you can find the two zeros. If you can find the two zeros, in other words, the first 0 is obviously 0 when you have a price of 0. The second 0 is when the price is so high that you don't sell anything at all. If you know those two numbers, then you know the price that maximizes revenue, and it's not too hard to actually find that price because you've got the equation for sales, which you could just plug it into that. And in fact, there's even more relationships that pop out here. If you notice, the maximum sales we got when we set the price to 0 was 3,800. Well, what's halfway between 0 and 3,800? 1,900, exactly the sales that maximize revenue. So not only is the price halfway between 0 and the intercept, the sales is also halfway between 0 and the intercept. And another way to even think about this problem is what you're actually doing is you're trying to find the area of a rectangle here. And this is one of the problems that you will encounter, be given, trying to find the area of a rectangle that fits in or is inscribed in a triangle like that. Because what is the area of that rectangle? It's a price times a sales. So what we're really trying to do is just maximize the area of that rectangle. And it's going to happen when the width is half of the maximum possible width and when the height is half of the maximum possible height. And all of these insights, all of these connections to other problems are kind of lost, or at least not even touched upon, using that very direct, quick method. So I really suggest you spend some time practicing this to learn this method.